Today in this video, we're going to be talking about a tool in probability referred to as Bayes' theorem. And Bayes' theorem truly is a theorem for calculating conditional probabilities when you can update it with further information. For example, and we're going to do an example of this actually worked out later on. Let's say that there's some sort of test that is performed, and the test comes back positive. Well, maybe, it's for some sort of disease, and you say, well, I guess, that person has that disease because the test came back positive. But the truth is, medical tests always have a chance of what's called a false positive, a chance that even though the test said is positive, it actually is not. And so there isn't actually a certainty that just because the test came back positive that the person actually has that disease. Now, if they take it a second time and it comes back positive, that totally changes everything, because now you've got one probability being based on a previous probability. And that's kind of partly where the advantage to Bayes' theorem comes in. Same goes with searches on your phone. Your phone keeps data on what you've already been searching for. So when you start to do a search, it's already using a programmed version of Bayes' theorem to look for things that you've been looking at or looking for or using to predict what possibly you're going to be looking for or looking at or using this time. So sometimes when you think, boy, my phone is smart, well, it's just probabilistic models. And one of the models used is Bayes' theorem, where we can update probabilities as we go. Now, I'm going to start off with an example. It's not a perfect example for Bayes' theorem, but it'll kind of get you thinking along those lines. And that would be, the example I'm using is, you're going to see a shot here where there's a Los Angeles Laker, the NBA basketball team, one of their players shooting a free throw. And I'm going to ask you now, I'm going to say, in your mind, just educated guess, what's the probability that you think a LA Laker, a professional basketball player, probability, and you're just making it up here, but a probability that they would make that free throw? And so here's the, and of course this is a GIF, so it's just going to loop through back, and you're going to see, of course, because you're going to keep missing. Now, if I was to tell you a little bit more about this player, and you may or may not remember this player, but this guy's name is Shaquille O'Neal. Shaquille O'Neal had made a name for himself as one of the worst free throw shooters of all time in NBA history. He was a horrible free throw shooter. His shot percentage free throws was 52.7%. Some said he would do better if he just shot granny shots. The point is, though, if I had told you at first that it was Shaquille O'Neal, some of you might not know who that is, but if you did, and as soon as I said the name, you would know, oh, well, he probably is going to miss the shot. Knowing one probability would affect your decision on another probability. Now, this isn't exactly Bayes' theorem, but it goes along these lines where we can use one probability to help us calculate a related probability to it. And so that's just kind of my way of getting you thinking about it. I do want to do a little bit of review here. The rare event rule, just because we are coming up on the end of this unit here, is that under given assumptions, the probability of a particular observed event is extremely small, then we would conclude that the assumption is probably not correct. We've talked about different kinds of probability. Relative frequency is the probability based off counting. Classical probability is the ones that have to be equally likely. Subjective is based off of relative circumstances or an educated guess, or maybe you want to call it an estimate. We had the addition rule, so you see the word or. This is going to show up today. The word or implies that you have to add the probabilities together. The word and implies that we're going to be multiplying probabilities together, and that's also going to show up today. Conditional probability, which most definitely we're going to be using today, is the probability of event A given event B has occurred. And there was a formula for that. We're actually going to take this formula and do what's called a derivation to come up with Bayes' theorem. So Bayes' theorem is going to be based off of our conditional probability model. The idea of the probability of at least one is 1 minus the probability of none, or the probability of it not happening at all is maybe another way to say it. One of our counting methods was permutations, and in that case, don't forget order matters, but in combinations, the order does not matter. We had the fundamental counting principle, which says if you got multiple events and each event can happen several ways, to get all the ways it could happen, you multiply the ways each individual event could turn out together, and you will get the total of all of them. And of course, we had the labeling problem formula. All right, so let's get back to Bayes' theorem. As I mentioned, we're going to see some of that review stuff here. Namely, here's that conditional probability definition. And part of it is the intersection, which when you talk about the intersection, that is the word and. So the probability of A and B. So of course, this has to do with multiplication here. The probability of a conditional event, probability of A given B has already occurred, is the probability of A and B, that overlapping part there, divided by the probability of B. We do have to consider the probability of B. Now, I'm going to do something kind of strange here. I'm going to flip-flop the A and the B. So here I've got the probability of B given A. Now, up here, we could say, well, that's, the probability of B intersecting A. But realize these two things are really the same thing. It's that overlapping part right there. It doesn't matter which one you put first. It's the overlapping part. So those two are actually really the same thing. And I'm going to do something that might seem strange in a probability setting. I'm going to do a little algebra here in a little derivation. I'm going to multiply both sides by the probability of event A, which of course then I can cancel these out. And I end up with that the intersection, the probability of the intersection, is the probability of event A and, or times, and the probability of B given A. Now I do that because now I can do a substitution. I can substitute this stuff in right there. So I'm going to be plugging it in right there. And we end up with this new formula. And this is Bayes' theorem, or Bayes' formula. That's what we're looking at here. The probability of A given B equals the probability of A intersected with, or and, the probability of B given A all over the probability of B. Now, at first glance, you're looking at it going, well, why in the world did you take something that was relatively simple and make it into something that's more complicated? Well, this is used in more complicated situations, quite frankly. And you're going to see that there's actually a lot of applications to this. But the main idea is that later on, I'll show you this, we can be updating our probabilities to continue to refine what the probability is going to be. Similar to what I was saying with the basketball example. If I told you who it was, if I'd updated your information, it would have changed your conditional probability of a LA Laker making that free throw. Bayes' theorem is a formula that describes how to update the probabilities of a hypothesis when given evidence. So you're going to see me do a lot of medical applications to this because that is one of the really big areas that uses Bayes' theorem. And typically the hypothesis is somebody has a disease or they're sick, given that a test came back positive. You're going to see me do several examples of that because this really is related to computer science, things like with your smartphone doing searches. Obviously, when you talk about artificial intelligence, this is going to be related to artificial intelligence stuff. But where most people see this has to do with the medical field. Sometimes it's written this way. The probability of a hypothesis given evidence is the probability of the hypothesis times the probability of evidence given the hypothesis over the probability of the evidence. In a lot of situations, this is known, where this one is not. So what I mean by, let's go back to the medical situation. The evidence, again, this would be the probability of the test being positive given when you know they're sick. That's actually something that's determined in studies, so they already know that number. Then they can calculate this number. All right, there is a more complicated version of it that's going to be used when people are sick, and this has to do with false positives and true positives, false negatives and true negatives. So I got to cover this, and then we're going to take the Bayes' theorem, what's called the simple version, and I'm going to tweak it a little bit to make something, again, a little bit more complicated, but I need that to fit some of the realities of what we're looking at. In any situation when medical tests are given, there's a couple things that could happen. If the test results are, say, positive and the person is sick, then we say that's a true result or a true positive. But if they're actually healthy, if they're not actually sick, but the test said it came back positive, then you would say it's a false result or a false positive. And that's this situation here. For most medical tests, if it comes back positive, most of the people will be sick. You know, there's people that haven't been tested and people that are tested, and when it comes back positive, most of the people tested are sick. But over here, there's always this chance that it comes back positive, but the person's actually healthy. And so that's a false positive. Then we've got the reverse. We've got the, what if the test comes back negative? Well, if the test comes back negative and they are healthy, that is a true negative. But if the test comes back negative and it's a few of these people that are actually sick, then you say that it is a false negative. So we could have a false negative and we could have a true negative. And those are the situations there. So when you take a look at Bayes' theorem, it's the denominator, which it was just the probability of the second thing. In this case, the probability of the test being positive. In that situation, we have to break it up into, well, it could be that it's positive because it's a true positive, or it could be positive because it's a false positive. And the key word there is or. It could be one or the other. So to get that denominator, we have to take a look at both of these situations, both of the probabilities of being a true positive and the probability of being a false positive is what we're looking at here. And so it does make Bayes' theorem, the formula, a little bit more complicated. I'm going to point this out right now, though. When it comes to calculating this thing, the numerator and the left side of the denominator, if you take a close look here, you'll see they're the exact same thing. So when we're talking about medical tests, that number there is going to get repeated right here. This will be a different number. We'll have to calculate that differently. But at least for running stuff through your calculator, it will speed things along if you realize whatever number you get for this, that's going to be the same exact number because they are the same thing. This is typically how it's written right here. Notice the negations above these. It means not, the probability of not being sick, which is what I mean here by healthy, times the probability of a positive test given not being sick. And again, we're talking about that false positive. The test says they're sick, but they're really not. So this is really the medical version of our, and it could be applied to lots of other things too, but so much of this gets applied to medical stuff. So I've kind of summarized here what I call the simpler version and the more complex version. They're both Bayes' theorem, or sometimes called Bayes' rule, or sometimes called Bayes' formula. If you need to Google stuff, you could actually use any of these three words and you probably would have stuff popping up. The simpler one, and then the more complicated one. The simpler one, you know or can calculate the probability of the events, so these two events here, and you know the probability of the reversed conditional. In the more complicated, well, I should have put this here. This is what we want when we know the probability of the reversed conditional. In the more complicated one, we know the probability of the events, and we can know or calculate the probability of the reverse conditional and the negation of the reverse conditional, the opposite of it. Okay, so let's start off doing some simple ones. We're using, obviously you can see the simple formula here. And we're looking at the old saying, where there's smoke, there's fire. And I don't know how much some of this stuff is true. This might be some of those made up statistics, but I'm just trying to get you to practice with Bayes' theorem here. So when the probability of fire, that means that there is a fire. Probability of smoke, of course, means we see smoke. Well, then the probability of fire given smoke means how often is there a fire when we see smoke. Probability of smoke given fire means how often we see smoke when given there is a fire. Okay? Here's some information. Okay, so far we can't calculate anything. You got to have some information to calculate using Bayes' theorem. If a dangerous fire is rare, so really what we're talking about here is a dangerous fire. 1% of the time. But smoke's fairly common. Smoke can be seen, let's use the number, and I don't know how true this number is, but 10% of the time, because there's smoke that comes from factories or maybe people burning wood to stay warm in the winter, things like that. And 90% of dangerous fires mean there is smoke. 90% of dangerous fires make smoke. There, let's see if I can get my words to spit out here. What is the probability that there's a dangerous fire when you see smoke? Now remember, dangerous fires only occur 1% of the time. Okay, so it's the probability of a dangerous fire given we see smoke. So it's just according to a recipe card here, you just sort of follow it. It's the probability of the first thing. Okay, so the probability of a dangerous fire. That's this one right here. That's going to be that 1%. And then it's the reversed conditional. So this is probability of dangerous fire given smoke. Do we know the probability of smoke given a dangerous fire? Well, we actually do. That's going to be the 90%. So that's going to be our 90% right there. And then on the bottom, it's the probability of the second thing. Well, the second thing was smoke. And I'm assuming, like I said, I'm not sure this is a real number, but the idea that you go outside and 10% of the time, if you were to cover the country, look at all the skylines, that the probability of seeing smoke is 10%. Okay, so that number is going to go there, which gives you a 9% chance that if you see smoke, it's a dangerous fire. So probability of a dangerous fire given that you see smoke. Basic example of Bayes' theorem. Let's do another basic one dealing with the weather. And this is here again, it's a little bit hard to sift through these. They're really kind of boring to read. But there's just information here, okay? 50% of all days that rain start off cloudy. And again, this could be just made up information. I don't even remember where I got it from. 40% of all days start off cloudy. In a dry month, only 10% of the days have rain. What is the probability of rain? And we're going to say during the day because all of this had to do with the daytime. What is the probability of rain given it's cloudy? Okay, so this is rain given cloudy. Okay, so the probability of rain times the probability of, okay, then we got to switch it. Cloudy given rain divided by the probability of the second thing, which is being cloudy. Okay, so it should look like something like this. So the probability of rain times the probability of cloudy when given it's got rain, and the probability of cloudy. So here we go. The probability of rain, 10% because it was on those dry months. So that's going to use that number right there. Then the reverse conditional. 50% of all days that rain start off cloudy. So I guess we're really talking about when it starts off cloudy here. So that's my reverse conditional probability. And then the probability of being cloudy, well, 40% of all days start off cloudy. So that's, of course, that one. And you end up with 12.5% probability that it's going to rain given it's cloudy. Okay, now let's get into a little bit more of the medical stuff. And we're going to be talking about, this topic is referred to as the reliability of a test. How much you can really kind of rely on or maybe believe a test. Remembering that there's such things as false positives. A certain virus affects 3 in 100 people. And this is just a made-up scenario here. A test is used to detect a virus, and a person is positive 85% of the time if the person has the virus. So notice it's not 100%. No test is 100%. Well, at least none that I know of. I shouldn't say that, but I'm going to say none that I know of. And 4% of the time when the person does not have the virus, that's our false positive right there. Let A be the event that the person is infected. So It'll be the probability of the person is infected given the person tests positive. That's part B, that the person tests positive. So the test comes back positive, that's given. Now I want the probability that the person is infected. If a person tests positive, determine the probability. Okay, so I basically said that, I'm sorry. Okay, so here's what it would look like as far as filling in Bayes' theorem. And again, if it's a medical one, you pretty much have to use the complicated one because of false positives. So it's going to be the probability of being infected. And if you noticed, I've tried to color code things so you can see where I'm going to get my information from. Times the probability of B given A, the reverse probability, which in this case is this one right here. Over, now remember I already mentioned this, these two things are identical. I don't have to calculate that left side of the plus down in the denominator. They're just going to repeat it because this is the true positive, which is what this is talking about up here, but this is the false positive. I have to do, it could be true or means to add, or it could be false. So the probability of not being infected, there's that bar, which means the reverse or the opposite, the complement, times the probability of positive given not infected. And that's the blue, you can see right here. 4% of the time the person does not have the virus, that's your false positive. Okay, so probability of not being infected, and then your probability of your false positive. Okay. So the 3 out of 100 is going to go here. The 85% or 0.85 is going to go here. Those two things get repeated. Not being infected, well, if 3 out of 100 are infected, then 97 out of 100 will not be infected in a general population. And then it'll be times the probability of a false positive. So that's where my numbers are all going to come from. Now there's some medical terminology here. You're not going to find this typically in your stats book, but if you do go on to study medicine, which I know some of you are thinking about doing, the green part here, it's referred to as the sensitivity. It's what percent of the time when confirmed by another test. So a test is somebody's tested and the test gives a positive or negative. Then they use a new kind of test or a different kind of test, and that one will also say positive or negative. If it says positive the second time, it's confirming it. Okay, and that's referred to as how sensitive is the test, or the sensitivity of the test. Just so you know, the higher the sensitivity, though, you might be increasing the amount of false positives. It might be like overly sensitive and say people are sick when they're not actually sick. So sometimes these two here, they kind of fight back and forth. Prevalence is how much of the population has this. If it's not real prevalent, then what ends up happening is, and you're going to see this in a couple of examples, your probabilities are actually really affected then by the false positives. If it's a low prevalence, those false positives really, really throw a monkey wrench into the calculation. And then we've got the specificity. Specificity is the measure of how well the test can identify a true negative. And that's basically this here. Okay, throw the numbers in. There we go. I already said what they were going to be. 3 out of 100, 85%, 3 out of 100, 85%, 97 out of 100, and 4%. Run it all through your calculator. And this is actually a 39.7% chance probability of being infected given that the test comes back positive. Think about that. The test comes back positive. People just assume, well, I'm infected. Well, in this particular example, there's actually only a 39.7% chance that you're actually infected. Mostly because this one has a very low prevalence. Anytime it's very low prevalence, the false positive rate is going to throw a monkey wrench. And what I mean by that, it's going to give you a really smaller probability than maybe what you thought it would be. Even though the sensitivity was 85%, this is actually a lot smaller. So I've got another one like that. I'm going to try and explain this to you why it works this way, because that's a little bit hard to wrap your head around. And I'm not sure that you'll quite get this. And I will warn you right now, the animation on this really doesn't work well. It's because I have so many dots in this picture. But here's the scenario, and you'll notice some little blue dots just showed up. But let's say that you test positive for a rare disease. I'm going to say rare being 1 out of 1,000. That you actually have the disease, okay? The test is correct 99% of the time. What is the chance that you actually have the disease? Okay, so you test positive for a rare disease, and you want to know if you actually have it. What are the chances that you actually have the disease? So here's you. You're the red dot. Now, because this thing does have false positives, now it's pretty good. 99% of the time. What that means, though, is that if this, you literally are seeing 1,000 dots here. I took a day and I drew all this out. Out of 999 other people, and I'm rounding slightly, just barely here, 10 would falsely be identified as having the disease. 99% of the time it's correct, but that means 1 out of 100 is not. So out of 1,000 people, that'd be 10. So then we take a look at you here. So there's 11 dots here total. There's these blue dots scattered around. And those are the people that give false positives. So here we go. There's those, and then there's you. That means that even though the test is correct 99% of the time, there's a 9% chance that you actually have the disease, which just seems crazy. But here's the truth. It's back to that prevalence. If the prevalence is really small, then the false positives really throw a monkey wrench into what you think might happen. So hopefully this helps you understand a little bit about when the prevalence is small, the false positives can really throw that in here. Okay, I'm going to do the exact same problem just without the picture. So here's how I would come up with the calculation. And of course, I'm using the more complicated one for this. So probability of sick, given the test is positive, again, it's a very rare 1 out of 1,000 disease, and the test is correct 99% of the time. So then when we go ahead and fill this stuff in, there's the prevalence, 1 out of 1,000 people. There's how accurate the test is, 99% of the time it's right. Remember, these two things just repeat because this is the true positive, this is the false positive. Okay, well then the not sick would be 1 minus that, 1 minus 1 out of 1,000, and the not being correct is 1 minus that. So when you end up calculating this, there's that 9%. So there's with the picture, there's without the picture. I wanted you to see that through the calculation, we actually really do get the same thing. All right. Here's where Bayes' theorem starts to shine, though. I know it's a lot of complicated stuff, but what if that person then goes back and gets a second test, has the test taken, exact same test, taken again? This is the beauty of Bayes' theorem. We can update the probability then. This then, instead of becoming 1 out of 1,000, it's 9 out of 100 is 9%. So we're going to change that because now we've got an updated percentage. So notice right here, this got updated, so did this. The accuracy of the test did not, or the sensitivity of the test, but the prevalence gets changed. And so then, of course, the probability of not right here will also get changed. So that turns out then, you take it the first time, there's only 9% chance that you actually are sick. But you take it a second time, and the test again says you test positive for the disease, that jumps way up to 91% because we changed drastically the prevalence of the disease from 1 out of 1,000 to 9 out of 100. So you'll see that in medical things where people will get tested, they'll find out they have something, but a lot of times they'll go back and they'll test them again, because the second time becomes way more definitive as to whether or not they actually have something. You might actually know people that have had the same test performed multiple times. This is why they do that. Let's take a look at something that everyone's a little bit familiar with, and that is COVID testing. And I'm going to say right from the start here, I've generalized a lot of these numbers. I did do some research But some of these are averages based off of other things. So at some point, I just sort of had to make it up. So my number I come up with at the end here, I would not put money on it. But at least it goes through showing you how this would work. Okay, so some information. The prevalence. I pulled off data off of a website on February 16th, 2021 to find out how many people in the United States that day. So on this particular website I look at, it gives how many active COVID cases are in a day. Of course, if they haven't been tested and they don't know they're sick or they're not showing symptoms, it doesn't really deal with it. That's why I tell you, my number here, it's going to be a number, but I wouldn't put any money on it. The specificity of the test, this was in a range, and I sort of just averaged out the range. So I'm using the number 98%. The sensitivity, again, this was a range. They based it off of several different tests, and it gave you different percentages for each one, and I sort of just averaged them out. So I'm putting here ballpark of the sensitivity. Okay, so we got to put in the prevalence, and the prevalence, here's how I calculated that on that day. Again, these were active cases, just the ones on the website. I wouldn't bet money on this. I took how many active cases in the US that day out of the population of the US that day. So that's my prevalence, so that's going to go here and here. Then we've got the sensitivity of the test, and like I said, that one came in at 80%, so I'm going to use 0.8 here and here. Now, the probability of not having COVID, well, it's going to be, 1 minus this number. So 0.972, 97.2% chance. If 2.8% have it, 97.2% don't have it on that particular day. And then I'm going to have the false positive here. Okay, so the the specificity is 98%. 1 minus that would be the false positive rate, or 0.02%. So now I have all my numbers, my prevalence, my sensitivity repeated, and then I'm going to have here my non-prevalence, my opposite of prevalence. The complement is what it is, and then the false positive rate, the 1 minus the specificity. Okay, we're running through the calculator. I would round that. I told you, don't put any stock into this number. I would round that to at best 50%, because I really don't want to rely on these numbers. I will say that I watched somebody else do a calculation that was similar, and they actually, now they had different day of the year, and they had some different numbers, but they actually came up with something real similar to mine. So I don't know. I have no idea how close I actually am, but I'm just showing you where it would be on that particular day. The actual numbers were really hard to find. I did the best I could, but that's what I ended up with. All right, I've been doing a lot of talking. I want you guys to give one a try. This is a different kind of test. This is one that has to do with an injury to your knee. It's called the bucket handle meniscal tear of the knee. And it presents itself in MRI. So the MRI is a test. It presents itself in MRI as a bow tie sign. I Googled this, and you can actually see it right there. It looks like a little bow tie. If you see that, then the MRI is saying, "Oop, you tested positive for this tear in your knee." They confirm it, though, through surgery. So this is one of those where I mentioned that sometimes you confirm a test. In this case, confirmed in surgery. And I've got a table here, just so you understand what's going on. So we've got positive tests, signs of the bow tie in MRIs, 38 that were confirmed surgically. And then here we've got tear surgically confirmed as not present. So the test was positive, but was not surgically confirmed. That would be a false positive there. And then, of course, we got negative. The MRI said no, they didn't have it. But, and when they had surgery, it also said no. Okay, so we've got totals there. What I'd like you to do is try this. I've got things mostly filled in here. Take a look at the table, pause the video, and see if you can come up with the probability of a tear given positive no sign. All right, so here's what we've got. Probability of a tear, 43. Okay, so here we've got 43 were confirmed surgically out of, well, out of 71. And then we're going to have times the probability of a positive no sign given a tear. Positive no sign given a tear, we're going to come up with 38 out of the 43. And now again, these two things, they just get repeated. And then for the probability of not having a tear, well, there were 28 after surgery, they didn't have a tear out of 71 patients. And then we're going to have probability of positive no sign given there was not a tear. So positive no sign given not a tear would be 10 out of the 28 right there. So you run that through, 79% chance, 79% probability. All right, I'm assuming that you're going to want to do some practice on this. There is going to be a worksheet in Schoology, and I will include an answer key for you to do some of these problems. Have a good day.